Hi there! This video series is to display my problem-solving and learning abilities. I plan to show that I can solve any programming problem, regardless of whether I already have expertise in a particular language. I hope this helps others in my field to learn not just how to solve a particular problem, but how to teach themselves a solution to an unfamiliar problem. Currently, I am learning Python. I have no professional experience in the language and have only been learning it since mid-January. My only formal training is completing the Python for Programmers course on Execute Program. While I'm picking Python up fairly quickly, I cannot claim any real expertise. Today, I'm vocalizing my thoughts while solving the 45th Project Euler problem. As always, I will link to Project Euler and my repo in the description. Let's dive in. Problem 45 is triangular, pentagonal, and hexagonal. Triangle, pentagonal, and hexagonal numbers are generated by the following formulae. Triangle is this, blah blah blah. It can be verified that the 285th triangle number equals the 106th pentagonal number equals the 143rd hexagonal number, which is 40755. Find the next triangle number that is also pentagonal and hexagonal. Once again, just to make my life easier, I am going to be copying the raw version of this problem. And we've done a bit. Even yesterday we did pentagonals. Or if you're watching this not the day it comes out, the previous video. See. This one I am going to fix the formatting to be a little more readable for my human eyes. Okay, so our approach, I think, can be very simple here. So we know that using Python and possibly many other programming languages, but we know for Python that we can generate numbers based on these formulas very, very, very quickly. So what I think makes the most sense, actually, come to think of it, we don't even quite have to do it the way I was about to say. So I was going to say we just generate like 1,000,000 of each of these numbers, but actually we don't have to. We can literally just go through various ends and see if the triangle, pentagonal, and hexagonal. Ooh, but we can't quite do that. So I was going to say triangle, pentagonal, hexagonal equal, but the n isn't going to be the same, obviously. So, except for the number 1. So what we need is similar to how we did in the previous problem, we created a way to find n based on a number. And in this case, it's actually going to be a bit easier for us because we won't have to go through 2 for loops. But first, we need to get our formulas. So, well, I suppose the very, very first thing we want is to grab these 2 lines. That way I don't have to copy them later. But we know from problem 44 that the pentagonal reversal equation is this, like, hold on, where did I put my good notes? This, because the whatever x is, which is the resulting pentagonal number, falls in equals this. So if we have x, we're trying to solve for n. We do some basic algebra here, break it down, and we come into this, which we can solve using the quadratic formula. And I've got it down here all set up, and I used the word sum here because that's the variable I was working with on this problem, but we don't quite have to do that. We just need this. Times x. And then we need to make the hexagonal formula in the same way. So it'll be x equals whoops, that's not what I want. I was copying the wrong one. 2n minus 1, right? Let's double check the actual problem just to make sure. N times 2n minus 1, which means x equals 2n squared minus n, which would mean that 0 equals 2n squared minus n minus x. Once again, we are going to convert to the quadratic formula, which I have here. Or convert using the quadratic formula, I suppose. So that'll be b is -1, -1 is 1, so 1 plus more inner parentheses, square root of b squared. Again, b is -1, so that's just going to be 1 minus 4ac, which is going to be 4 times -1, so -4, and then c is always negative, so we'll do -4, or sorry, that's actually 4 times 2. So 4 times 2 is 8, ca is 2. 4 times 2 is 8. The negatives cancel out, so it's actually 8x in our case. And then I'm just going to continue this, making it Python style, so that I can just copy this here in a minute. Do I have too many parentheses? Open, 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 close, close, close. Okay. And then 2a is just 4. So our complete hexagonal formula for finding n based on x is that, well, this is technically plus or minus, so throw that in there. Okay, so all we have to do is for n in range. And I'm going to go ahead and start with 286. I don't have to do it this way, but since we already know that we have this 285, and we want to find the next triangle number, we know we need an n of at least 286 for triangles. And actually, I am going to go ahead and say n equals 286, and then I'm going to do a while true, and of course it can be, while true loops have a very good chance of potentially being infinite loops. So we might not want it to do this. I'm actually going to say I'm actually going to change this to n equals 285 and then plus equals 1 being the first line of the loop. And that is because when I go to print this, I want to be able to do something like number for n equals n. And I don't want to have to do any sort of off by one error thing. Found triangle number for n equals n of n equals n, and I'm going to say t equals 0 because I'm just going to hold this, and I'm going to say p of n also 0 and h of n also 0. Actually, I'm just going to say t of n here, and the goal is to populate each of these. Or, wait. Yeah, so t is the triangle number, and we want to have p's n here. Maybe not. I'm going to change this to n of p and n of h so I don't confuse myself again. Equal to Pentagonal number for n equals n of p. Oops. And why is that parenthesis still there? Hexagonal number for n equals n of h. Okay. I think that I can do that. Okay, so n plus equals 1, t equals this is our first formula here. So t is equal to n times n plus 1 divided by 2. And then let's go ahead and create a def find in p takes in a p, which is the potential pentagonal number, and then return x, I guess. Obviously that isn't going to work. We'll have to actually build out our method, but for right this second, we're just going to do it this way. And then n of p equal to find n of p for t, and n of h is equal to find n of h for t. And then we're going to say if n over p is greater than, I'm going to say greater than 0, I think. Yeah. And n of h greater than 0, we're going to break. And that should be all of the logic that we need for the main part. Now we got to build out these two little methods, because currently the way they're written, they make no sense. So n1 is, for the pentagonal, we've got an n1 of this, and an n2 of this, and we replace our x's with our p. Nope, don't want that. And then similar to what we did here, we want to see if n1 is greater than 0 and an integer. I think that's all we need to figure out. And I'm going to go ahead and do a third check here. So if n of 1 greater than 0 and n of 1 mod 1 equals 0, so it's an end. Whoops, wrong buttons. And I'm gonna say n1p is I might not want to do that, actually. I was going to do in a check where I didn't, like, calculated the p for n1. And I think, yeah, maybe I still will. But for right now, let's actually do this way. So I am building in an assumption that all of our math is perfect. Which, because this is a computer program, it should be, but also I wrote it. So I'm always a little bit like, I could have made a mistake in my algebra. That's not outside of the question. It's happened before. So I am currently building in this assumption that if we get an n1 or an n that is both positive and an integer, we have found the correct answer. I think that is how that works, but we shall find out, I suppose. Actually, now that I'm thinking about it, I'm gonna have a different is valid n. And I'm going to say to return n greater than 0 and n mod 1 equals 0. So what am I doing here? I'm just making it so that I call this function instead of having these multiple checks. I believe that I could simplify this here with, like, a complex ternary, but I think this is fine. It's plenty, it's plenty clear, I think. And then we're actually going to just kind of copy these two lines here. So for pentagonal, or for hexagonal rather, we have this. And obviously we want this to be n2. This will be the positive one, this will be the negative one. I have a feeling that it's only ever going to be n1, but I don't know that for sure, and I don't want to go through the mathematical proof to, like, show that it definitely is. But in any case, this has a runtime of n, so it's constant, so that's really, really good. It should be pretty efficient for us. Let's find out. And it was very efficient, except actually broken. Okay. Well, that's fine. Okay, found triangle number for n 55385 to be this, which is technically a float, but that's fine. I am actually... okay. I take it back, it's not fine. Whoa, what did I do here? And you can see it ran in about 1/10 of a second. That time it took a little longer. It's fine. So found triangle number for n equals this to be this, which is equal to pentagonal number for n equals this, and hexagonal number for n equals this. Now, going back to the problem, find the next triangle number that is also pentagonal and hexagonal. So I think we want this number here. Oops. Come on, Project Euler. There we go. All right. So our general strategy worked as soon as I got it programmed correctly. Basically, just go through every n starting with 286, find the triangle number, check whether it is also a pentagonal and hexagonal number by calculating what their n would be if it were, and then just printing out our findings once we have one that's in all three. So yeah. I'm going to call it there for today, and I'll see you in the next one.